Hello, in this video, we're going to be talking about atomic energy levels. We're going to talk about the electrons in an atom now and how they can move about to different energy levels, we'll call them, by interacting with light, by interacting with photons, particles of light. All right, so here we go. We're in topic 7.1 officially. We're continuing our atomic physics fun. Okay, chemistry students rejoice because this is what we're talking about. We're talking about orbitals. We're talking about where electrons can be in an atom. So fun. Let's just remember our basic picture of an atom so far. So remember, in the nucleus of the atom is where we have all our protons and neutrons. This picture is very much not to scale. Remember, the nucleus is very small. It's like 1/100,000th the size of the whole atom across. So not to scale at all, but we got, a really dense nucleus. That's where the positive charges, protons, and also neutrons all smushed together, held together by the strong force. And zinging around the outside somewhere are electrons, which are teeny tiny in comparison. But they're flying around the outside. All right, so this is just two example atoms just for fun. Chem people, you may remember or know that electrons might arrange themselves like this in something more exciting like neon, which has 10 protons, 10 electrons. I can have 2 really close. I can have 8 further away. All right, fun. We don't even really need to get into that level of detail in physics. We keep things real simple, and we're not going to usually get more complicated than hydrogen, like 1 proton, 1 electron. Trust me, it gets confusing enough if we really dig into it and what's going on and why. But that's the idea, is there's these different orbitals. A good kind of analogy is to think about planets orbiting. All right, it's a little loose and it doesn't totally work. We'll talk about how, but to get a picture in your head, it's pretty good. Just picture, Mercury, Venus, Earth, Mars, blah, 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 all orbiting the sun at different distances. The idea is there's different amounts of energy. We're just talking potential energy here, so there's different amounts of energy between them. Yeah, and based on the distance, they'll be orbiting with different amounts of energy. All right. The one main difference is Mercury. The planet Mercury could be anywhere. It's wherever it is right now, but it could be at any distance. There's no rule saying it can't be, there couldn't be a planet halfway in between us and Venus. But electrons don't work that way. These orbits are set by nature. So there's only certain orbits electrons are allowed to be in. The electron basically has to be in this kind of energy level orbit, or this one, or this one, or this one. There's only a couple allowed orbits for electrons. That's something that we observe, and we'll get more into it in HL when we do some more quantum stuff and talk about the work of one Mr. Niels Bohr. But for now, good enough to say that there's only a couple orbits that they're allowed to be in. Each orbit, the main thing that we care about, even more so than distance, because that gets kind of fuzzy, is energy level. All right, so think about different amounts of potential energy, as in we're just talking electric potential energy. So, you got 2 charges, maybe separated by some distance. In a basic way, I could just think about using Coulomb's law and our equations in topic 10 for HL students of how much potential energy you have between 2 charges. Just like having potential energy between 2 masses that are separated by some distance, right? I have different amounts of potential energy between these 2 charges as I do between, say, these 2 charges. So I get more or less different amounts of potential energy at these different orbits. So an electron that's in this lower energy orbit might have more a certain different amount of potential energy than an electron out here. All right, so each orbit corresponds to an energy level, which means the energy levels are quantized. These are discrete amounts of energy that these orbiting electrons can have, because the electron can be orbiting here, what we're marking as K, and for physics, we're not going to need to worry about these letters so much, but the electron could be orbiting here at K, or it could be orbiting at L, but the big idea is it can't be orbiting in between. It's not allowed. So you can only have certain amounts of energy. You can't have an amount of energy in between K and L. You just can't. They don't fit. All right. So that's what we're finding and what we're going to look at. The idea that the energy levels in the atom are quantized. This is just a word for basically they come in discrete chunks, discrete amounts. They're not continuous. They are discrete. All right. So let's get into that. Here's what they look like for hydrogen. You don't need to memorize these. They'll be given, or HL students, we're going to get to an equation where you can come up with these. It's super fun. But these are numbers for how much energy you have at different orbits. All right, so this is kind of what it looks like. It's similar to an idea we've talked about a little bit about gravitational potential energy. Again, most similar to the HL topic when we do this crazy stuff, like we say there's zero potential energy at infinity and negative everywhere else. All right, so we're going to be dealing with negative potential energies, but this is what it looks like. Negative 3.4 is bigger than negative 13.6, right? So we're just getting closer to zero. If I could take an electron and get it up to zero potential energy, that would be the ionization energy. So that's how much energy it would take to completely pull the electron away from the influence of the nucleus. Okay, but so these are the different amounts of energy that the electron has in those different orbits. So just picture, in one state, so say we have the ground state here, it has like negative 13 electron volts of energy. Then in the next level, it has like negative 3 and so on. All right, so these are the amounts of energy that the electron has when it's orbiting at these different energy levels. And notice they're quantized. So again, the electron can have negative 13.6 electron volts in hydrogen if it's in what we call the ground state, or it can have negative 3.4 electron volts of potential energy, or this much, or this much, or this much, but it can't have in between values. So you won't have an electron in the hydrogen atom that's got a potential energy of, say, negative 10 electron volts. It's just not allowed. There's no space for it if you want to think of it that way. There's nowhere for it to fit. All right, how we name these is a little confusing because we use n equals 1, n equals 2, n equals 3, n equals 4, n equals 5 for the different kind of energy levels, but then we make it confusing by saying n equals 1 is the ground state. Fair enough, probably makes sense. That's like the lowest energy level. And then if it gets excited, it gains some energy, it gets excited. Well, we'll call this the first excited state, but you can maybe see where this is going to get confusing because that's n equals 2. N equals 1 is not the first excited state, it's the ground state. Right? The second excited state is n equals 3. Oh boy, so just watch out for that, but that's how we name them. We'll practice with that. Okay, also remember, you need to be able to convert between electron volt and a joule. It's not in your data booklet, so remember how to do this. All right, that's how many joules are in 1 electron volt. Okay, so here's a good picture to have of what's happening, because here's what can happen. An electron can move in between those energy levels. And how does that happen? How does the electron get the energy to jump up an energy level? Or if it drops down an energy level, how does it get rid of that energy? Well, the secret is light, and the secret is photons. Particles are packets of light. Remember, is the idea of what a photon is. So electrons use photons to jump up and down in energy levels, and it looks like this. You can see at some point now it's got high energy, gives off an electron, drops down an energy level, absorbs a photon, now it jumped up. So those squiggly lines are representing photons. So it's at a high energy level now, just dropped down, it emitted a photon. And then if it absorbs some light, it can jump up. All right, so they get energy from light or they give off energy as light. That's the idea. Some fun things that happen. This is truly spontaneous because we said the electron's not allowed to be in between the energy levels. Well, guess what? It's not. It does not move between the space between levels. In this kind of first model that we're talking about, the electron literally moves from here to there instantaneously. It disappears from one position and reappears in a different position. It does not pass through the space. It simply is one place and then it's in another. If that's confusing, it should be. All right, it's kind of crazy, but that's what happens. The electron can't move in between the space. It spontaneously moves from one energy level to the next immediately. All right, we might do some stuff later that helps explain that a little bit, but that's the idea. All right, because these energy levels are quantized and it can only have certain amounts of energy, it has to gain or lose the exact difference in energy level. That's going to be the key thing. It's the difference in how much potential energy the electron has here to how much potential energy the electron has here. It must be giving off or gaining exactly that much energy for it to move, or else it has a different amount of energy than these energy levels allow, and it won't do that. Okay, so the idea is if it absorbs a photon like that, then it can move up to a higher energy level. A higher energy level is always going to be further away. And if it emits a photon like that, it'll drop down to a ground state. So just think about conservation of energy. If it absorbs a photon, it's gaining energy, so it's going to move up an energy level. And if it's in an excited state and it wants to just, chill out, drop to a lower energy level, it'll give off some light, spit out some energy as a photon, and then it's got, less energy at the end. The main thing we got to do is just deal with a bunch of differences. Then we're going to talk about delta E, the difference in energy between two energy levels. And the key idea is that the photon is the carrier of that energy. So the difference in energy level has to equal the energy of the photon emitted or absorbed. So we'll look at that with an example to kind of clarify it, but that's the idea. Okay, one other thing you'll need to do is we're going to be dealing with wavelengths a lot because we're talking about light and colors of light, and we'd like to talk about wavelengths. So here's another equation in the data booklet. This one, 7.1, we want to know this one at this point. This is the energy of a photon. The energy of a photon is Planck's constant times the frequency of the light that is, making the photon, if you want to think about that way, the frequency of the light that goes with that photon. So frequency of green light or blue light or ultraviolet of a certain frequency, whatever. Remember our classic equation, the wave equation, that wave speed, c, the speed of light for an EM wave, equals frequency times wavelength. That's topic 4. You want to be okay with that one. So since the speed of light equals frequency times wavelength for an EM wave, I could replace frequency with the speed of light over wavelength. And that's a data booklet equation. All right, so this is just the equation with Planck's constant, the energy of a photon equation. Instead of being in terms of frequency, it's in terms of speed of light. So there you go, very kind of the IB. They don't even make you turn back to topic 4 to find the wave equation. They baked it in to this equation twice. All right, so this one will be useful for doing some of the stuff that we're going to do. All right, but it's just this equation and the wave equation. All right, so let's do an example to illustrate. Let's say I have an electron jumping from the second excited state of the hydrogen atom to the first excited state by emitting a photon. We're going to find the wavelength of the photon that was, that should say emitted. Sorry, emitted, because we're dropping down. So find the wavelength of the photon that was emitted. All right, if you want, pause the video, try this on your own, see if you can apply those ideas that we just talked about to solve this. The answer's down on the bottom right. Okay, hopefully gave it a shot. Here we go. Main idea is I got to find difference in energy. So I have a photon, an electron that's emitting a photon and dropping from the second excited state to the first excited state. All right, the tricky part about this is, remember, n equals 1 is the ground state. N equals 2 would be the first excited state then, right? It's like the first time it's up an energy level. And then this would be the second excited state. So I'm jumping from n equals 3 to n equals 2. So I'm dropping from here to here, from 3 down to 2. So I want to find the change in energy between them. I'm officially doing final minus initial because that's how I should always do a change. So final, I end up down here. I started up here. I dropped down, right? So I have a change in energy of negative 1.88 electron volts. We're going to drop the negative in a second because this is physics and we just use our brains and think about, what the math means. But do think about what this means. Delta E being negative means the electron lost energy, and because the electron lost energy, it must be giving that energy off in the form of a photon. So the energy of the photon, since the electron lost 1.88 electron volts of energy, the energy of the photon is positive 1.88 electron volts. It won't ever be negative. So just if you absorb and you gain energy, think about what that means versus a photon leaving and dropping down. All right, but so the energy of the photon must be equal to the energy. So the electron lost 1.88 electron volts of energy. That energy gets carried away by a photon. So the photon has this much energy. For using the equations I'm going to use and dealing with stuff like, I want to eventually get to something like nanometers at the end for a wavelength. I want to go back to base units. So we're going to turn electron volts back into joules with this conversion. All right, so is that many joules? I'm not worried about sig figs to the very end. Don't round anything until the end whenever you're doing math. Don't round away your answers. Okay, so now that I know the energy of the photon, I can use this equation. This is the energy of a photon equation in terms of wavelength. It's super convenient. You could absolutely just set this equal to HF, find frequency, then go to the wave equation to get wavelength from frequency. This equation does all that at once. Okay, so you're going to take Planck's constant in the data booklet, times the speed of light, constant in the data booklet, divide by the energy of the photon we just found, and bam, boom, there you go. All right, 6.612 times 10 to the minus 7 meters with sig figs, since I got 2 sig figs and somewhere this conversion, my answer needs to be 2 sig figs, 660 nanometers. All right, so that's a wavelength of light that comes off if you go from here to here. Well, hey, guess what? That's light we can see with our eyes. That, I think, is like red light. All right, so when in a hydrogen atom specifically, that's the main one we'll look at, but every atom has its own different set of transitions that are possible. And just to show you, this is what we'll get into next time, and we'll look at some of these for real in the classroom. But you can see these different possible transitions. There's only a few. There's quantized, right? It can't do everything. It could go from 3 to 4, 3 to 2, 4 to 2, 5 to 2, 6 to 2, maybe 3 to 1, 4 to 1, blah, blah, blah. But there's a certain amount of them. Um, here are 4 different possible transitions that happen in the hydrogen atom. So 4 different colors of light that can come off of a hydrogen atom if the electrons are moving around. So next time we'll look a little bit about that, how these different colors are kind of fingerprints of different atoms, different elements, and how we use that in physics. All right, but there you go. There's the idea. Electrons, they jump up, they drop down. Photons are the things that do them. Energy of the photon equals the difference in energy between your energy levels. And that's pretty much how you do atomic transitions problems. So have fun.